Okay, so here we've got our 4.3 notes. So while you're listening to this video, make sure that you're taking notes on your paper and actually writing the stuff down so that you make sure that you understand it and can learn it and can do these problems in the homework. Feel free to pause it if you need to, rewind, don't fast forward. First thing we're going to do is the warm-up, which is find the function with the given derivative whose graph passes through P. So we've got this derivative, f prime of x equals negative 1x squared. And we want to know what is the, what function creates this derivative that passes through the point 2, 1. So quickly, I want you to think about why do we have to specify a point that this function passes through? Why do we have to tell it exactly where it goes through? Think about that real quick. And then let's find this derivative. So when finding this derivative, we know, or we're not finding the derivative, when we find the function, we're going backwards. So this is x to the negative 2. So we could say that we know that the original function was x to the negative 1. And here we've got negative 1. So if we take this function, we take x to the negative 1 and we find the derivative of it, we would get negative 1 times x to the negative 2, which is what we have right here. Now remember, we have to add that constant because there's an infinite number of functions that have this antiderivative. We have to add this constant so we know exactly which one we're talking about. And that's where this point comes in. So the next thing that we do is we plug in, or we substitute 2 for x. So we've got 1 over x, and then 1 for y, plus c. We solve for the constant, therefore we get c equals 1/2. And so that tells us that our function is f of x equals 1 over x plus 1/2. Now try this one on your own, see if you can do it, using the same idea. Think about what the exponent must have been in the original function. In the antiderivative, what is the exponent there? So it should be x to the 1/4. And if we think about taking the derivative of this function, we've got 1/4 times x to the negative 3/4, which is what puts our derivative down here. And we add our c, then we plug in, we substitute to find c, and we get f of x equals x to the 1/4 minus 3, because c equals negative 3. All right, next in our presentation, we've got a bunch of, well, this is just a way to find, kind of a generic way to find antiderivatives, right? If we've got f prime equals x to the n, then we know that f, the original function, is going to be x to the n plus 1 divided by n plus 1. Since when we find the derivative of f, we would multiply times n plus 1. Next, we've got some homework answers. We'll go over these later. Now we're going to talk about the first derivative test for local extrema. So this kind of adds to our study of graphs and how we can tell whether they're increasing, decreasing. We'll start talking about concave up, concave down, ways that we can really learn more about graphs by using their derivatives. So the following test applies to a continuous function only. So the function has to be continuous. And so first we say at a critical point C, okay, so we're talking about the critical points. Remember, the critical points are when the derivative equals 0 or when the derivative does not exist. If f prime, if the derivative changes sign from positive to negative, so the derivative here is starting positive, and then it becomes 0, and then it goes negative, then f has a local maximum value at C. So that's our first derivative test. We say if it's negative before C, and then it becomes it's positive before C, and then it becomes negative after C, then it's going to be a maximum. All right, so going from there, we have the same idea, except this time, if f prime changes sign from negative to positive, then we know it's going to be a minimum at C. So here we've got negative derivatives, 0 derivative, and then positive derivatives. Negative derivatives, no derivative right here at this corner, and then positive derivatives. There are situations in which f prime does not change sign at a critical point. So that could be like here, we have a horizontal asymptote, or sorry, not horizontal, but a horizontal line, horizontal tangent. And here we have a corner, and the derivative is not changing sign, but there's still a critical point that can happen. We've also got some endpoint tests. So if we're at a left endpoint, so we're at A, if the derivative is less than 0 for all the values greater than A, so our derivative is less than 0 for values greater than A, then f has a local maximum or minimum. Minimum if the derivatives are greater than 0. That means that we've got a minimum at A. That's at a left endpoint. At a right endpoint, it's going to be the opposite. We're going to say that if we've got our right endpoint B and the derivative is negative coming down into B, then we've got a minimum value. If the derivative is positive coming up to B, then we've got a maximum value at that endpoint. And we can call those endpoints local maximum and minimum values. All right, let's do an example. So we want to determine the extreme values of f of x and describe where it is increasing and decreasing. So the first step is we're going to find the derivative of the function. So for this one, we used the product rule. We got the derivative of the inside, or derivative of the first one times the second, plus derivative of the second, e to the x, times the first. We're going to simplify by factoring out the e to the x, and then we're going to factor this polynomial. And the reason why we want to factor it is so that we can find the critical points. So there's no place where this function is going to be, where the derivative does not exist. So we're only looking at places where the derivative is 0. And that's when this equation right here is going to equal 0, which is at -3 and 1. So our critical points are at x equals -3 and x equals 1. Okay, our next step is to make a sign chart. So we put our critical points down and we think about, okay, when x equals 0, let's go back up here. When x equals 0, this is going to be 1, and we're going to have 3 times -1, -3 times 1, so it's going to be negative when x equals 0, so that makes this negative. And then we could think about what happens if we plug in like a really negative number. Let's say we plug in like -100 here. That -100 is going to get squared to make it positive, so this is going to be a positive number. E to the -100 is also going to be a small positive number. So this graph is going to be positive in this section. Same thing in this section right here. It's going to be positive when x is a really big number. And I'm going to stop here. I got to upload another video because my space limit is about to run out. So we'll pick up right here in the next video.